you. Thank you, Larry. And I really would like to begin by thanking the organizers for giving me this opportunity. And I'm very excited to stand here today and share with you some new results that we think are exciting. And this is a collaborative effort. The group at my company, AASC, and then our collaborators for this work at JLab and Professor Gang Seo, who's our subcontractor from Norfolk State. And I see two people in the audience who deserve a lot of credit, Genfa Wu and Anne-Marie Valente Feliciano, who before this work were strong collaborators with us, and they should be acknowledged because we've made a lot of progress thanks to their involvement too. So what I'd like to do is say a word or two about who we are and then what motivates our getting into this field. A little bit about our energetic condensation coating devices, some RRR measurements, which is the source of some excitement, to compare our coating approach with other coaters to see whether there are some insights that might be gained, and then, time permitting, and I think it will permit, show you some crystallography and metallurgy that we've done of these films, and talk about future plans. So the company itself, I founded it, 16 years ago, and we do things that might broadly be categorized as pulsed plasma devices. They're pulsed plasmas of one kind or another. We've done a lot of microelectric propulsion for NASA and the Air Force. We sell diamond radiation detectors. We recently are building, we're right in the middle of these projects for Homeland Security, a very novel, very fast, pulsed, high-intensity neutron source that we think has some applications in Homeland Security, in finding special nuclear materials, and possibly high explosives. And that's going on. And then, of course, there's our thin film work, which itself was an outgrowth of some work we dabbled in with Andre many, many years ago in trying to lay down refractory coatings on the inside of ethylene cracking furnace tubes. And I was pleased to hear Enzo on Monday allude to this application. We actually are right in the middle of that and hope to make some progress in that. So that's what my company does, and we have 8 employees. It's a very small company with 5 PhDs, and we have a lot of fun. What motivates this? Andre said he would skip over this slide, and therefore, so should I. This is like bringing coals to Newcastle to tell you all why thin films might add some value. However, I was very excited coming in here to put this bullet in, that the ultimate payoff would be from cast aluminum cavities with higher temperature superconducting films on them. But regrettably for me, as you all heard, Enzo has already thrown some cold water on that idea. And but he still hasn't thrown superfluid helium on the idea. So there may be hope. There may be hope. So what's this collaboration? JLab has begun a 3-year DOE-funded project to actually do some thin film development in a systematic manner. And Charlie Reese told us about that on Monday. My company has received a companion 3-year grant. And so the idea was, and we have some other SBIR grants to study niobium-3 tin, molyrhenium, and other such exotic Group 15 things. So we've established a collaborative agreement under which we use our coaters to lay down various thin films, and then we take advantage of the excellent suite of metrology that's available at JLab and with Professor Gang Seo, who's a subcontractor to us, who works closely with the JLab group, in order to advance our understanding. And as Larry put it on Monday, the idea is to learn what properties does a thin film have ideally, to sort of systematize that to the extent that we can, that would make it well suited for an SRF coating, to make it defect-free, and then worry about how to actually optimize the tools that we have. And the tools might well be high PIMs or ECR sources. They're not necessarily these cathodic plasma sources. I'm not wedded to those. What am I wedded to? I'm wedded to the idea of advancing our understanding and having fun along the way, and hopefully being a little heretical in order to keep Enzo happy. So Why do we collaborate? Well, the answer is very simple for those of you who've heard it not once, but twice already from Enzo. He did it on Monday, and he did it again at the banquet last night. So that's why we collaborate. But I couldn't resist, since he talked about an allusion to some recent movie with that Australian actor in it. I couldn't resist going back and doing a little history last night. And a great American patriot, Thomas Paine, was reputed to have said in the thick of the American Revolution, "Men, we must hang together, or assuredly we will all hang separately." And so the funding for our thin film R&D, we all know, hangs by a thin thread. So please, let's hang together. So what's our approach? I've already told you that. It's to do things in a systematic way. Walk before you run. Let's lay things down on coupons. Let's use all these tools. Let's try and improve our understanding. Then graduate to facilities like the surface impedance characterization facility that Charlie described, and that we know there's another one at Cornell. There's similar cavities at SLAC. But to take advantage of those tools, to take our best films on copper substrates, for example, or niobium, and put them in those cavities and get the next level of electrical impedance data, and finally converge on being able to do some serious cavity demo. So a few words about the coating facilities that are available at AASC. We have this large chamber here which shows a cavity outside it that can actually accept the whole cavity if we needed to, which we call the CED. We have a new facility that we just built. It came into operation last month, which we call CAD, which is simply cathodic arc deposition. And then we have this variant on it, which is all too familiar to Andre, who is one of the pioneers of this technique. It's taking the plasma, bending it through a magnetic filter, and in this case twice. So we have an S filter. And the idea is that unwanted macroparticles would come flying straight here and get lost, and only the plasma would be guided by the magnetic field and impinge upon the substrate. So that gives us an option, if macroparticles turn out to be a problem, to actually deal with them. The CED consists of a chamber like this. Everything we do is at a vacuum of at least 2 × 10⁻⁸. So we do take pains to approach UHV. I say approach because when I was at Yale, I had a colleague who came into my lab, and I was very proud to tell him that I had a vacuum of 6 × 10⁹. And he looked disgusted because his vacuums were 10 to the minus 11. He said, that's UHV. So everything is relative. And you have a molybdenum cathode and a coaxial moly mesh anode. And in this case, in this B field of just 100 Gauss, the arc sort of executes a kind of a helical dance here. And it takes about 40 milliseconds to go from there to there. And so if you have either a tube that you're trying to coat or just a substrate here, this helix, as it spins around like a spoke, dwells on the substrate for just a millisecond. And in that millisecond, we are laying down about 4 angstroms. So it's a monolayer of niobium in 1 millisecond. Now, why is that significant? Perhaps it isn't. But I'd just point out that 1 monolayer in a millisecond, recall the old adage from graduate school days of 10 to the minus 6 torr means 1 monolayer in 1 second. Well, 10 to the minus 8 torr means 1/100th of a monolayer in 1 second. But if you're actually growing your film in a millisecond, you can see that you're leaving precious little time for any impurities and things like that to get embedded in there. So that might be something significant. And if you do some very simple bookkeeping from the measured film thickness, you can actually work back to the cathode and deduce an erosion rate 40 micrograms per coulomb, or we're boiling off 600 micrograms of niobium and turning it into a plasma, which I should add. And by the way, those erosion rates compare very favorably with Andre's measured rates for similar materials, titanium, platinum, zirconium. The interesting thing about this device is it's making a plasma that actually has a temperature in it, if you wanted to call it that, of about 40,000 degrees Kelvin. So it's a very, very different phase. And then you're condensing that out onto the substrate. So any information, so this notion, we use RRR of 30 niobium, and we're producing films with triple R's of 300. And that's not a surprise. It's not a surprise to me, because you're completely transforming the raw material into this plasma state and then recondensing it. So why should it have any memory of where it came from in the first place? The other thing about energetic condensation is, as Andre explained from that Thornton diagram, the growth models and so on, you can see that at low energies you have one kind of growth, and as you get to the medium energy, which is where we are, we get more columnar heteroepitaxial kind of grain growth. And then if you put some pulsed biasing on it, which we have the capability to do, as Marcella Bilek had shown, these compressively stressed films from cathodic arcs, by applying a pulsed bias, you can actually relieve that stress, and you can get strain-free coatings with the right combination. And the exciting thing about doing a pulsed bias, as Andre explained, is that it now gives you a different knob. You have a macro pulse of a millisecond, which has certain properties, but within that, you can apply micro pulses. And if you look at the energy of these cathodic arcs, Andre's measurements in aluminum has a big spread from 40 to 180 EV. Some Australians measured niobium between about 50 and 120 EV. So these are very energetic ions that are rattling the lattice and modifying the surface that they hit as they condense. The CAD device, I'll just briefly say, its role is it gives us some flexibility in two ways. One is by varying the current. We've designed this thing to run at either 200 amps per pulse or 5 kiloamperes per pulse. What that allows us to do is to change the deposition rate, where we can grow fractions of a monolayer or many, many monolayers per pulse. And I'm just curious to systematically understand, is that important? So that's why we did that. We have this custom pulsar that allows us to apply up to 8 kilovolt pulses if we so chose in microsecond little slices or longer, and vary the duty factor and so on. So we can do some very systematic pulse biasing studies. Now, we are funded by DOE to look at niobium-3 tin. And what are we trying to do? By contrast to the approach here, which I was very excited to see what you've achieved with bringing the oven inside the chamber and then heating it up to 1300 C, as we learned yesterday, is that we're taking a completely different approach. We're taking this target and splitting it into two separate targets. There's niobium, and there's tin next to it. And we can actually cant them so that we can point the plasmas towards one another at the substrate and so on. And we can also take our pulse forming network, and by simple modification of it, we can actually split the current. So we have a knob to turn here, where we can have more current going to the tin than to the niobium. So at the source, you can produce more tin than niobium. And at the substrate, which is heated, you're going to accept more niobium than tin. And so you can play that game, hopefully. And what's the goal? The goal I want to look at is by pulse biasing, and by doing this dual target approach in a high vacuum, by the way, this would also be at a 10 to the minus 8 torr. Can we accomplish what might be impossible, actually? Can we get niobium-3 tin in the right phase without having to post-anneal it? Because we're using essentially a non-thermal approach to growing the compound. We're starting from very energetic ions and forcing them to stick together to form this compound. Will we succeed? Who knows? Should we try? Well, on Monday we got permission to try from Enzo via Monsieur Giordano.